One. Hi class, today we are talking about sinusoidal derivatives. So this is the derivative of sine and cosine. Okay, so we're going to go through in your note kind of developing why the derivatives of sine and cosine are what they are. And then we'll look at composite functions of sine and cosine and just do some differentiating because why not? It's fun. So this note really is just to show you, like I said, the derivatives of sine and cosine, and you'll still be expected to know all of the rules you knew before, the product rule, quotient rule, chain rule. Now being able to incorporate sine and cosine within these rules. Okay, so you should have for here the graph of sine. Okay, and underneath it, I put the graph of cosine because the derivative of the sine curve is actually cosine, but I'm going to explain why. So if you want, you can go ahead and pause the video and copy what I've done here with these red tangents, as well as these blue dotted lines. So what I'm doing here is showing you that the slope of the tangent at each point along a sine curve is actually corresponds to the y value of the cosine curve at the same point. So notice at x equals 0 or theta equals 0, the slope of this tangent would actually be 1. Okay, if you calculated that. And notice down here, the y value of the cosine curve is 1. Okay, notice now that we have a positive slope of the tangent as theta goes from 0 to pi over 2. But notice that even though it's positive, the slope is decreasing in magnitude. So here you go, cosine is positive, but it's decreasing, just like the slope of the tangent, until it gets to a slope of 0. And here we have a y value of 0 at pi over 2. Similarly, here we have that now the slope of the tangent is negative, and it gets more and more negative as we continue from pi over 2 to pi. So notice that cosine is negative and gets more and more negative as well until it gets to maximum slope, or I should say minimum really, of -1. So here we also have in cosine a y value of -1. Again, sine, the slope of the tangent of sine now is negative, but becomes less and less negative as we go from pi to 3 pi over 2. And that's what happens with the cosine curve until it again hits a slope of 0, which is a y value of 0. And now the slope of the tangent is positive and increasing from 0 to 2 pi, which happens here as well. Okay, until we get to a slope again of 1 and a y value of 1. So that is an analysis visually of why the derivative of sine x is in fact just cosine. So now we can use that to determine the derivative of these following functions. Okay, so here we have x times sine x. So we think about this as a product rule first and foremost. We have two functions, x and sine x, that are being multiplied together. So the derivative is, again, the one just stays the same times the derivative of the other, plus now the derivative of the first times the normal second. So let's take the derivative of x first, and that's just 1. And then we multiply it times sine x, plus, now we leave x the same, and multiply it by the derivative of sine x, which is just cos x. So really, this is just sine x plus x cos x. Okay, now I noticed here that I put sine x squared and sine squared x to make sure that you guys know the difference. So sine x squared is like you're taking the sine of x squared, but sine squared x is like you're taking all of sine x and squaring it. So these are two different things. Okay, so here we have a composite function, okay, the sine of x squared. So we're going to use the chain rule because it's a composite function. So I'm just going to use y prime. So you take the derivative of this, which is cos x squared, And then you multiply it by the derivative of what is inside, the inside function. So that's just 2x. So we would write this as 2x out front and then cos x squared. It's how that would typically be written. Now this derivative, though, is the chain rule where we think about a function to the power 2. So we bring the 2 down, keep the inside the same, reduce this by 1, and then multiply by the derivative of that inside function. So this is actually 2 sine x cos x. Okay, so hopefully that makes sense to you. This is just, you can think about this as blah squared. So we're just doing, the derivative of that is 2u times u prime. That's what we did, just the chain rule. But in this case, you think about it as sine blah. So the derivative of that is cos blah times blah prime. Okay, if you have questions about that, let me know in class. Okay, so now we have cos x, and its derivative is actually negative sine x. So I have the two graphs set up for you right on top of each other, and I would like you to, on your own, right now, complete the same analysis of cos x to negative sine x that I did between sine x and its derivative. So go ahead and take some time to look how I did it on the first page, and I want you to complete the same analysis to reason why the derivative of cos x is negative sine x. Not sine x, but negative sine x. Okay, so do it now. I'm looking at you, I can see you. Do it. All right. Okay, so now that you did that, we get to, what if you have something like this, the y equals cos 3x? Well, just think about this as y equals cos of blah. So then the derivative of that is going to be negative sine blah times blah prime. Okay, it's a chain rule problem. So of this, we'll get y prime equals negative sine 3x times 3. So you can bring the 3 out front, so you just get negative 3 sine 3x is how you can write it. Sorry, that x shouldn't be there. There, negative 3 sine 3x. There we go. Okay, so the rule then is these composite functions. So if you have sine of f at x, so whatever is inside the argument is a function other than x, then you do what we've been doing. So it's cos, and then you keep f at x the same, and then you multiply that by f prime at x. So the Leibniz notation for that then is the derivative of sine f at x, where we're treating x as the variable, is the derivative of sine f at x, where f at x is the variable, times the derivative of f at x, where x is the variable, dx. Okay, so that's the Leibniz notation, which is the same as this. So similarly for cos of a function, where your argument is a function, then your derivative is negative sine of that function, okay, times the derivative of that inner function. Okay, so similarly, the Leibniz notation I'll write down here so I have more room. So d cos f at x dx is equal to the derivative of cos f at x df at x, so with respect to f at x, times df at x, the derivative of f at x with respect to x. Okay. So let's just do a few more examples that illustrate this. So our next one is a cosine function that has an inner function. So we take our derivative of cos is negative sine. We keep the inside the same, and then just multiply by the derivative of the inside. Okay, and then we want to just scoot that guy out front just for better form. So minus 3x squared sine 1 plus x cubed. Okay, and then this next one here, you got to think about, this is first and foremost a quotient rule problem. We have a quotient. So when we do y prime, you can do it below. I just want to make sure I have enough room. You think about the bottom times the derivative of the top. So the top is cos 3x times 3. Okay, so now we do minus the top times the derivative of the bottom. So remember, that's cos x all squared. So we bring down the 2, then we leave cos x the same, and then multiply it by negative sine x, because that's the derivative of cos x. And then all over the bottom squared, which is cos to the power 4x, because cos squared x squared, then you have an exponent of 4. So this can be slightly written kind of better, but notice here, you might want to collect this cos x's, but you can't because the arguments are different. You might also think that you can common factor out a 3 because there's a 3 here and a 3 here, but you can't do that either. Actually, the only thing that you can common factor out is a cos x. So I'm going to give more space here. So you can actually factor out a cos x since there's one here and there's one here. But then after that, you're pretty much out to lunch. So you get still have a, I'm going to bring this 3 out here. So you have a 3 cos x cos 3x minus, but then there's a minus here. So that becomes a plus sine 2, I'll bring the coefficient out front. I already factored out the cos x, so sine x sine 3x. That's an x. All over, and then end the bracket there. All over cos to the power 4x. So then we can cross off one of these and one of these. So you have it like this. So just this on top with cos to the power 3x on the bottom. Okay. So now let's move to example 4, where we want to determine the equation to the tangent of this function. So x cos 2x at pi over 2. So the equation of the tangent, so the tangent is always a line, so that's just y equals mx plus b. So we need to find the slope of this line by finding the derivative at this x value. So let's do our derivative. So y prime equals 1. So that's the derivative of x. And then cos 2x we leave the same. Plus x. And now we take the derivative of cos 2x. So that's negative sine 2x times 2. Okay, since because of the chain rule. All right, so let me simplify this a bit. So we get cos 2x minus 2x sine 2x is really the best way to write that. So now we can sub in pi over 2. So at x equals pi over 2, y prime equals, so then we get the cos of pi, right, because 2 times pi over 2 is pi, minus pi times sine pi, because I'm just subbing in pi over 2, but it's being multiplied by 2 every time, so that's why that works. Okay, so the cos of pi, if you remember, is negative 1, and sine of pi is 0, so you just subtract 0, so you get a value of negative 1. So that is the slope in y equals mx plus b. Okay, so now I need to sub in my x, which is pi over 2, and my y. So my y occurs when I put pi over 2 into this function, which gives me negative pi over 2 when you go ahead and do that. So now I'm going to sub that into y equals mx plus b. So negative pi over 2 equals negative 1 times pi over 2 plus b. So if you solve that, b equals 0. So the equation of my tangent is just that, y equals negative x. So if you want to bounce over to GeoGebra, change this. This is the function x cos, oops, so when you do this, you got to do x times cos 2x, okay? So there is that function. Isn't it pretty? I think it is. So at pi over 2, so you can do the tangent, comma, and then I can find pi over 2, the function f. There we go. You can see there it's equation right there. Y equals negative.
Could I please get student parliament members to come help with pies? That's student parliament members. Thank you.
Anyways, you can see it there. Okay, so that just confirms what we just did. Awesome. Doesn't that feel really good? Okay, so now one last task. We want to find the maximum and minimum of this function over this interval. So now we're just going to do where we set the derivative equal to 0 to find possible max and mins. And then we do the first derivative test, okay, basically. Actually, we're not even going to do the first derivative test. You'll see what we do. Okay, so f prime at x is just 2 cos x times negative sine x. So we can just make that minus 2 sine x cos x and then set that to 0. So minus 2 sine x cos x equals 0. So, I mean, we can divide out the negative 2 if we want. You don't really need to. But you'll see you have sine x and cos x equals 0. Okay, so that means that either sine x has to be 0 or cos x has to be 0. And remember, this is on the interval from 0 to 2 pi. So you can either think of what these curves look like, or you can think about the unit circle. Sine x equals 0 anytime where y is equal to 0. So that would be at 0, and again at pi, and again at 2 pi. Or again, you could think about the sine curve when it hits the x-axis. And then cos x is equal to 0 anytime where x is 0. So that's at pi over 2 and at 3 pi over 2. So all 5 of these are possible maxes and mins. They're solutions to the equation where the derivative equals 0. So what I did here is I set up a table of x and the actual function, not the derivative. So here are my 5 numbers in order. Okay, and I actually put these into the function. So when you put this into the function, you get 1. When you put this into the function, you get 0. This you get 1, this you get 0, and this you get 1. So the max is actually equal to 1. So that occurs at x equals 0, pi, and 2 pi. And my min is 0, which occurs at x equals pi over 2 and 3 pi over 2. So again, you can head over to GeoGebra and verify that this is true. Cos squared of x. That's what it looks like. And you can see from 0 to 2 pi, which is just about 6-ish, where the maximums and mins are. So there's your max, there's a max, there's a max, there's your min, and your min. So there you go, guys. That is the derivative of sinusoidal functions. So again, probably the biggest challenge will be incorporating all of the other rules you've learned together with these new derivatives. And also, I know there is some problem solving and even some optimization in this homework. So I hope the video was informative. Thanks for watching. I hope you learned lots.